The unyielding tether, why humanity may be forever bound to the solar system. The human imagination, that restless engine of aspiration, has long been captivated by the glittering expanse beyond our terrestrial cradle, the grand ambition of interstellar colonization, the dream of becoming a true multistellar species. We speak of the Alpha Centauri flyby, the terraforming of exoplanets orbiting distant G-type stars, the very colonization of galaxies. Yet, as our scientific understanding deepens, as the sheer, brute physics of the cosmos asserts itself against our fervent desires, a sobering, perhaps even melancholic, conclusion begins to crystallize. Humanity, for all its ingenuity, may very well be cosmically tethered, our ultimate destiny confined to the gravitational well of Sol, the very solar system we currently inhabit. This is not a statement born of pessimism, but rather one rigorously derived from the interlocking constraints of relativistic physics, energy economics, material science, and the chilling realities of evolutionary biology operating across astronomical distances. The fundamental barrier, the immovable stone in the path of interstellar migration, is the tyranny of light speed. Einstein's special theory of relativity, an edifice of modern physics confirmed across countless experiments from particle accelerators to the precise timing of GPS satellites, dictates that no object with rest mass can attain or exceed the speed of light, often denoted as c, which is approximately 299,792,458 meters per second. While this speed limit seems abstract when discussing journeys measured in light years, its implications for space travel are devastatingly concrete. Proxima Centauri, the nearest stellar neighbor, lies a mere 4.24 light-years away, a distance that translates to approximately 40 trillion kilometers. Even if we could conceive of a vessel propelled by a fusion drive operating at a hypothetical 10% of the speed of light, the one-way trip would consume over 42 years. This duration immediately collapses the very notion of maintaining a continuous, culturally coherent human society during transit, a phenomenon already hinted at in the paradoxes of time dilation. Though at these lower interstellar velocities, the time dilation effect on the travelers themselves would be minimal compared to the subjective time experienced by those left behind on Earth or in the solar system. Consider the energy requirements for achieving even modest fractions of c. The kinetic energy of an object is calculated using the formula 1/2 mv², where m is mass and v is velocity. To accelerate a mere 100,000 kg spacecraft, the mass of a modest interplanetary probe today, to just 1% of the speed of light requires an energy input approaching 1.125 times 10 to the power of 17 joules. To put this colossal number into perspective, this is roughly equivalent to the total annual energy consumption of a medium-sized developed nation, expended for a single, one-way acceleration burn. Scaling this up to a generation ship carrying perhaps 1 million people, along with the necessary resources for long-term closed-loop ecological support, a mass perhaps 100 million times greater, the energy needed becomes almost unimaginable, necessitating the complete, sustained harvesting of a significant fraction of the Sun's total energy output over decades, a feat far surpassing the projected capabilities of any foreseeable Dyson swarm or advanced stellar engineering project. Current propulsion concepts, such as the theoretical breakthrough Starshot directed energy sail, which aims to push tiny, gram-scale probes to 20% of c, rely on focusing the entire power output of an immense terrestrial laser array onto a sail the size of a postage stamp, a technology completely unsuitable for macroscopic, crude vessels. The sheer inefficiency of accelerating mass against the universal speed limit acts as an insurmountable energy tax on all interstellar ambition. Furthermore, the journey itself is not merely about reaching the destination, it is about surviving the transit. Interstellar space, despite its apparent emptiness, is a hazardous environment for prolonged exposure. Cosmic rays, high-energy particles originating from supernovae and active galactic nuclei far outside the solar system, pose a severe threat to biological organisms and electronic systems. Shielding against these relativistic particles requires vast amounts of mass, more mass that then requires exponentially more energy to accelerate. A few centimeters of lead or water can effectively stop most galactic cosmic rays within the relatively benign environment of the solar system, protected by the Sun's heliosphere. But in the deep interstellar medium, the required shielding thickness to maintain acceptable human radiation dosage limits, often cited as around 1 millisievert per year, would demand armor plating so thick it renders the vessel prohibitively massive. The alternative, active magnetic shielding, requires generating magnetic fields strong enough to deflect charged particles, demanding immense onboard power generation capabilities that further compound the initial energy problem. Then there is the issue of impactors. Even dust grains traveling at fractions of c possess staggering kinetic energy. A speck of paint chip, no larger than a few micrometers, striking a hull at 10% of the speed of light, releases energy comparable to a small explosive charge, potentially leading to catastrophic hull breaches or the vaporization of sensitive equipment. While computational fluid dynamics models suggest techniques like plasma buffering shields might mitigate some of this risk, these too require continuous, enormous power expenditure, further stressing the already astronomical energy budget. If we pivot away from the relativistic limits and consider the biological imperative, the problem deepens. The duration of interstellar voyages, even at optimistic speeds, stretches far beyond the comfortable span of human cultural memory and biological viability. A journey lasting centuries, even a millennium, necessitates a true generation ship, a self-contained, perfectly closed-loop biosphere capable of sustaining complex social structures, technological maintenance, and genetic diversity across countless cycles of birth and death. The historical record, even within the relatively stable confines of Earth, is replete with examples of societal collapse, cultural drift, and technological regression over far shorter timescales. The maintenance of complex systems, nuclear reactors, life support recyclers, genetic sequencing databases, for millennia, without access to external raw materials or specialized expertise, borders on the fantastical. Imagine the technological gap between the great-grandchildren of the launch crew and the arrival crew, separated by 200 subjective years, who might view the founding generation's technology as arcane or even mythological, a recurring theme in science fiction but a very real threat to mission integrity. Furthermore, the genetic bottleneck associated with launching a small initial population presents an existential biological risk. To maintain sufficient genetic diversity to avoid crippling inbreeding depression and to ensure resilience against novel, unpredictable pathogens that might arise in the closed environment, geneticists estimate that a minimum viable population size, the minimum viable population or MVP, needs to be in the low thousands, perhaps 5,000 individuals, to maintain long-term evolutionary health. Launching such a population, along with the necessary industrial base to support them across generations, pushes the mass of the required vessel into the realm of planetary engineering, not merely starship construction. This brings us squarely back to the solar system. Within our own stellar domain, the rules change dramatically. The energy required to travel between, say, Earth and Mars, or even Earth and the Oort cloud, is orders of magnitude less than that required for even the nearest stellar departure. The tyranny of C is effectively circumvented, replaced by the manageable constraints of chemical, nuclear, and potentially advanced fusion propulsion systems. The gravitational gradients are shallow enough that orbital mechanics become the primary tool, not continuous thrust. Data transmission, while still subject to latency, a few minutes to Mars, several hours to Jupiter, remains fast enough to maintain a cohesive, though geographically distributed, human civilization. Crucially, the solar system offers a virtually infinite supply of raw materials, asteroids, the ice moons of the outer planets, the vast material reservoirs of the Kuiper Belt and Oort cloud, allowing for the growth, repair, and expansion of human infrastructure without relying on the impossible logistics of interstellar transport. The infrastructure being developed today confirms this internal focus. NASA's Artemis program, China's Tiangong space station and Chang'e missions, And the rapid commercialization of low Earth orbit by companies like SpaceX and Blue Origin are all fundamentally focused on mastering the physics within the Sol system. They are learning how to manage closed-loop life support for months or years, how to mine lunar regolith for oxygen and propellant, and how to operate complex machinery remotely under high radiation environments. These are all necessary precursors not for interstellar flight, but for building a true, resilient, multi-world solar system civilization. Consider the trajectory of resource utilization. The concept of the resource base drastically shifts the probability curve. On Earth, we are constrained by terrestrial chemistry and ecology. In the solar system, the asteroid belt alone contains trillions of tons of metals, iron, nickel, platinum group metals, enough to build 1 trillion Earth mass equivalents of infrastructure. The icy moons of Jupiter and Saturn offer near-limitless quantities of water, essential for radiation shielding, life support, and rocket propellant synthesis through electrolysis. Utilizing these resources, known as in situ resource utilization or ISRU, transforms space travel from a logistical nightmare of launching everything from Earth's deep gravity well into a manageable process of in-system manufacturing and relocation. Every kilogram manufactured on the Moon or Mars requires vastly less energy than launching that same kilogram from Earth. This efficiency inherently favors expanding within the available energy gradients, which are steepest locally and decay rapidly with distance from the Sun. The concept of a sphere of influence is critical here. This sphere is currently capped by the practical limits of propulsion technology, which struggles mightily beyond the gravitational influence of the Sun, say, out to the very edges of the Kuiper belt or perhaps the inner Oort cloud, where the gravitational potential energy differences become too vast for conventional propellant-based systems to efficiently traverse within human timescales. Moving beyond this, into the realm of the nearest stars, we transition from navigating a local neighborhood to crossing an ocean without the possibility of mid-voyage course correction or emergency material transfer. The scientific exploration we undertake now already suggests this binding. Missions like Voyager 1 and 2, which are now traversing interstellar space, are functionally one-way trips. Voyager 1, launched in 1977, is now over 24 billion kilometers from Earth, communicating across distances that require immense power from its radioisotope thermoelectric generators and taking over 20 hours for a one-way signal transmission. These probes are collecting invaluable data about the heliosheath and the local interstellar medium, confirming the harshness of that environment, yet they are sending back data derived from instruments designed decades ago, operating on dwindling power, utterly incapable of course correction or carrying substantial samples back to humanity. They are scientific flags planted at the edge of our reach, not the vanguard of colonization fleets. Their success underscores the immense technical difficulty of merely sending an inert object across the boundary, let alone a complex, living ecosystem. Furthermore, the very nature of scientific discovery encourages deeper commitment locally before attempting distant leaps. The search for extraterrestrial life has overwhelmingly focused within our own system, evidence of past water on Mars, subsurface oceans on Europa and Enceladus, methane cycles on Titan. These worlds offer accessible targets where the potential payoff, the discovery of a second Genesis, is immense, and the travel time is measured in years, not centuries. The engineering required to drill miles beneath the ice of Europa, for instance, is immense, but it is an engineering challenge solvable with terrestrial industrial capabilities applied over decades, entirely within the solar system's logistical framework. The risk of failure on a Martian habitat is devastating locally, but the failure of an interstellar arc means the permanent, unrecoverable loss of a fragment of humanity and its accumulated knowledge. The risk aversion inherent in preserving the species will always favor the near-term, near-energy cost solutions. Let us consider the theoretical warp drive concepts, the Alcubierre metric or similar spacetime manipulation theories. While mathematically compelling within general relativity, these solutions invariably require the manipulation of exotic matter, matter possessing negative mass energy density. to create the necessary space-time distortions. The existence of such matter remains purely theoretical. It has not been observed, and creating it in any meaningful quantity seems to violate established quantum field theory principles, particularly the average null energy condition, which governs the behavior of classical fields. Even if exotic matter could be synthesized, the energy required to create a stable, macroscopic warp bubble capable of enclosing a starship is estimated, in some theoretical models, to approach the mass energy equivalent of Jupiter or even the entire Sun. Thus, the dream of bypassing the speed of light limitation dissolves back into the insurmountable hurdle of energy economics, just as fusion rockets stumbled against the kinetic energy barrier. The discussion then pivots to the concept of digital existence, the uploading of consciousness, which some proponents suggest bypasses biological constraints and reduces the mass of the traveler to near zero, thus making interstellar travel trivial. However, this theory founders on two massive, unresolved scientific issues. First, the physical mechanism of consciousness itself remains one of the great unsolved mysteries of neuroscience and philosophy. We do not possess a functional, verified theory of how the electrochemical processes of the brain give rise to subjective experience, the hard problem of consciousness. Second, even if we could perfectly map and simulate a human brain, a feat requiring computing power exponentially beyond exascale machines, the transmission of that data across light years would still be limited by the speed of light. A digital signal traveling at sea still takes 4.24 years to reach Proxima Centauri. While this avoids the radiation and lifespan issues of biological travel, it exchanges them for communication latency so extreme that a cohesive society across stellar distances becomes impossible. The explorers would exist as distinct, non-communicating entities separated by years of real-time lag. Furthermore, the development trajectory of humanity demonstrates a clear pattern of mastering proximity before attempting distance. We mastered navigation across oceans before attempting to cross continents reliably, and we mastered continental flight before contemplating global jet travel. Within the space domain, we spent decades mastering low Earth orbit before attempting the Moon, and we are now spending decades establishing permanent bases on the Moon and Mars before even designing the prototypes for true Jovian or Saturnian outposts. This iterative, resource-constrained scaling strongly implies that the technological and societal maturity required for interstellar travel, the ability to deploy terawatt-scale power systems, maintain complex synthetic ecologies for millennia, and reliably shield against relativistic hazards, will only be fully achieved after humanity has already fully colonized and diversified across the entirety of the vast, resource-rich solar system. The colonization of the outer system, the establishment of self-sufficient habitats on Titan, the mining of the ice moons of Jupiter, the eventual construction of massive, spinning orbital habitats utilizing materials harvested from the Kuiper Belt, will take centuries, perhaps millennia. These endeavors represent the logical next step in energy expenditure and resource capture. They build upon existing physics and chemistry. By the time humanity has achieved total mastery over the solar system, when we have perhaps constructed a localized Dyson swarm around the Sun, efficiently channeling its entire output, the sheer scale of our local infrastructure, powered by an entire star, will dwarf any hypothetical starship. Why would a civilization capable of managing the energy of a star use a minuscule fraction of that energy to launch a small fraction of its population on a perilous, centuries-long journey when it can continue to thrive, expand, and innovate within the perfectly tailored gravitational and energy environment it has already mastered? The final consideration is the concept of homeostasis in societal evolution. Civilizations tend to anchor themselves where the energy balance is most favorable. The Sun provides a fixed, stable energy source for billions of years. The nearest stars are similar, but the journey to them represents an active decision to impose massive instability, radiation, isolation, resource scarcity, and existential risk upon the population undertaking it, all to reach a slightly different, fundamentally similar energy gradient at immense temporal cost. It seems far more probable that the mature, stable, Technologically advanced human civilization will choose the path of least resistance, maximizing the utility of the energy and material bounty already available within the solar system, utilizing the vastness of the Kuiper belt as its raw material buffer and the orbits of the planets as its habitable real estate. We will become a vast, distributed, solar system civilization, interconnected by near-light-speed communications within the system, but ultimately, forever orbiting our parent star, the unyielding tether of physics and economics holding us fast in our cradle. The stars will remain beautiful, aspirational points of light, but they will be the domain of distant probes, the messages we send out when we have truly mastered everything here, never the destination of our children. The greatest human expansion will not be outward into the void, but inward and outward across the vast, rich expanse between Mercury and the Oort cloud, making solar eternal, comfortable, and ultimately necessary dominion.